Hello everyone. In this video we are going to look at two famous ensemble learnings. One is random forest, which is basically a collection of decision trees that is used to reduce the variance on the individual decision trees. And the other one is the adaptive boosting or AdaBoost method, which is another ensemble. And we're going to talk about these and how to basically use these two methods to improve the accuracies in general and metrics for a classification task, although we can use them for regression as well. So here, for a decision tree, what I need is I need the decision tree itself from the Scikit-Learn tree, from the Scikit-Learn ensemble. I need the random forest classifier. I want to artificially create some classification data, so I bring the make classification method from under Scikit-Learn datasets. I bring the train test split from under model selection, and then I bring under metrics the classification report, which is a beautiful method, and it gives you the precision, recall, F-score, and everything in one single command instead of you individually calling them and getting those numbers. So it can make the code much shorter. So random forest is a collection of decision trees, and basically you use the bootstrapping resampling, which basically it creates samples from an original sample, resamples with replacement, and each time gives a new set of data to your trees, and then train the trees, and then the collection of the trees is used to reduce the amount of variance in the total classification, because you know that one of the things that your decision trees are weak at are variance. They have smaller bias but high variance, and they are prone to overfitting, right? So I mentioned in the previous video on decision trees that one of the methods to reduce this chance of overfitting is to do pruning. Right now in Scikit-Learn there is no pruning, but I said that another method is to use the collection of these, and that is called the random forest that we're going to see here, and that acts like a regularization. So if you use a random forest, we don't really need pruning, and I'll show you that here. So here I go ahead and make 400 samples using this make classification. I use 20 features in that, and this is another interesting thing about this function is I say out of these 20 features, only 8 of them are really providing real data. The rest of them are like linear combination of the other data. They are like noise or something, and we really only need to focus on 8 of them. And this is something that you can get from your PCA, right, or principal component analysis. Which one of the features are really showing the variance in the data? Just focus on those. So one of the things you can do in general, and that you're going to see in my next video, is do a principal component analysis on your data and get only those that describe the variance and only perform your machine learning on those. So here I'm letting know my training or my data creator, classification creator, that hey, only 8 of them are going to show the variance, the rest of them are not that useful. Then I'm going to split my training and test data, and I use 30% for testing, 70% for training, and break my X and Y data, and where X are the data and Y are the targets, into X train, X test, Y train, and Y test. Then first I pass the training data to a single decision tree. So I use my decision tree classifier. You know, it has a bunch of parameters that I mentioned in previous video, but here for simplicity, I let Scikit-Learn use all of the default values for the maximum depth, for the number of leaves, for the minimum decrease in impurity, and so on, right? I discussed them in one of the previous videos. So here I go with all defaults. I create the object, the classifier object, I fit it to my training data, and now that the decision tree is formed and all the parameters are calculated, now I pass my X test with the predict method to give me my predictions. Okay, so on my 30% data of test, I get my predictions, and then I pass my predictions and the actual labels Y test to my classification report to give me the measures, right? Like precision, recall, F score, F1 score, and so on. And then I repeat the exact same thing here, but this time instead of one decision tree, I pass it to a random forest. So I say, create for me the random forest classifier object. How many trees do I want in it? Here I use 150 trees. And then the default for bootstrapping is true, okay? If this is false, then all of your data is going to be used to train all of the trees, which is not really the best thing you want to do. You typically want to keep this bootstrapping as true, and that is the default. So even if I didn't say this, it's going to be true, not false. I just wanted to show you that, hey, this bootstrap, you can turn it off or on, but I don't recommend you turn it off. So here I'm going to use 150 trees. Now the number of trees in a forest is a big parameter, okay? The more trees you use, the better the estimate you're going to have at the expense of what? A lot of computations. So here I'm going to use 150 of them, fit that random forest to my training data, make some predictions with it on the test data, and then pass the predictions and the Y test to the classification report again, see if the random forest gives me any better numbers than what? Than a single tree. So let's go ahead and run it, see what we get. So here we go. There we go. You can see that out of 120 data, which is 30% of 400 numbers, out of those, I have two classes here, and the precision for me, the overall weighted precision is 0.76. Recall is 0.76. FS score is 0.76. But if you look at my numbers for precision, recall, and FS score for the random forest is 0.84. So I have some considerable gain in the accuracy, right? In general, precision, recall, even I can add accuracy measure alone. Right now, if I make this 150, 250, you probably expect the number to go up a little bit more, right? So let's go ahead and look. You see? There we go. So now, if you look, my numbers are significantly better, right? My numbers are quite a bit better, although on the tree, a single tree, they are also better, right? But in general, you clearly see the difference between here and here, right? And it comes at some computation cost, but you clearly see that with 250 I could go all the way up to like 93% precision and recall, which is really significant. Okay, so this is a random forest, and then we have AdaBoost, where adaptive boosting or AdaBoost, this is another ensemble which you bring a bunch of classifiers or regressors. The important thing about both the random forest and the AdaBoosting is that they are both collections of a homogeneous set of classifiers or regressors. Random forest is by nature homogeneous. It's just a collection of trees. But for AdaBoost, it's the same thing. So if you bring a bunch of regressors or classifiers, they have to be the same thing. You cannot combine different types of classifiers together. There is a third method of Ensemble called stacking, which we are not going to see in this video, but that the stacking or blending is where you can combine, like, for example, a decision tree with, let's say, a logistic regressor or classifier or something like that. But here we have to combine the same classifiers, and the default is also decision trees for AdaBoost. So here we're going to use decision trees. From Ensemble, I'm going to bring AdaBoost classifier. Everything else is like my previous code. The make classification, train test split, and classification report. Again, I'm going to make some data, right? And then I split it into training and testing, just like previous case. I use a single tree to estimate it, and then I use the AdaBoost classifier to do estimation on it. Again, I need the number of estimators. Here I use 200 estimators to create my classifier, my AdaBoost classifier, fit it to the data, predict the flags or the targets for the X of test, and then compare it to Y of test to give me what classification report. So we want to see whether boosting is going to get you a better result than a single tree. But what is boosting? Before I run the code, what is boosting? What's the difference between that and the random forest? So boosting means what? And what is adaptive boosting? So first you go ahead and give equal weights to all of your training data, and that way you train your basically estimators. Okay, so what you create is called the weak learner, which is a little bit better than something random. Okay, a random classifier. And then what would you do? You look at the training data, see which one of the training data was classified correctly, which one was not. For those that were classified correctly, you bring their weights down, and for those that were not classified correctly, you bump up their weight. You add to their weights adaptively until your estimators are getting better and better at classifying the data that were not previously classified correctly, until you finally make a strong learner. The theory of boosting, I am going to make a separate video on that, but just the idea here is different. It's working on the weights of the data and then adding to some of them and reducing the weights, some of the weights, okay, based on whether they have been classified correctly or not. So it's a separate method, and this AdaBoost is a popular ensemble. So let's go ahead and run this. And here you can see that this is your tree and this is your ensemble, which is about like 3% better than that. And you can change this number and change your performance. Of course, you're not going to get the same number each time because the data here are generated randomly, and the split is also random as well. And here you have 10 features that are informative out of 30. That's plenty of features that provide data. If this guy goes down, probably your tree is not going to perform as great as it did right now. So you're not going to get mostly the same results over and over, but what you can probably see is the ensemble is doing a better job than your single tree does. So hopefully this video was useful to you, and I'll see you in my next lecture. Thank you.